parámetro que tenemos que tener en cuenta es si estoy trabajando con una solución adecuada. ¿Por qué apunto a esto? Porque cuando empezamos nuestra clase de hoy, lo que vimos es que teníamos la hipótesis de que la solución estaba muy diluida, de manera tal de que cada nanopartícula dispersa la luz una única vez. Entonces, una cosa que se suele realizar, que se acostumbra a hacer, es hacer cubetas con soluciones a diferentes concentraciones, de manera tal de conseguir un rango que vamos a llamar el rango de concentraciones buenas, en el cual lo que obtenemos como diámetro característico o como parámetro de tamaño característico de estas nanopartículas es constante. Cuando está demasiado diluido, probablemente el equipo me dé poca información, me dé información errónea. Cuando entro en el rango de concentraciones adecuadas, todos los diámetros que yo obtenga van a ser aproximadamente semejantes, considerando las incertezas correspondientes, pero a partir de cierta concentración, lo que voy a ver es que debido a estas dispersiones generadas por scattering múltiple, ¿sí?, voy a empezar a tener señales que no corresponden a lo que estábamos observando, ¿sí?, al diámetro adecuado. Entonces, si uno quiere conocer y hacer una caracterización exhaustiva de la síntesis que está realizando, lo que tiene que hacer es este proceso de estudiar por DLS a diferentes concentraciones.
To understand this point, we have to remind that DLS theory relies on the fact that we are working at sufficiently low concentration to have simple scattering events. And this means that when a photon is diffused by is scattered by a nanoparticle and reaches the detector, it has gone directly from the nanoparticle to the detector without meeting another particle in between. And in this case, we have a phase difference of the different beams, which is related to the position of the nanoparticles, as we have seen at the beginning of this presentation. Now, if you increase the concentration, you will have multiple scattering events, which means that a photon will meet several nanoparticles before it reaches the detector. And in this situation, the theory of DLS is not valid anymore. So if you do DLS experiments at two concentrated regimes, you're going to analyze the autocorrelation function you measure using a wrong theory, which is based on single scattering events. And in this situation, you will underestimate the dimension of your nanoparticles. Of course, you can analyze the autocorrelation function in presence of multiple scattering events, but in this case, you must not take into account the theory of DLS, but you must work in the framework of the theory of diffusing wave spectroscopy. And if you're interested in this, you can have a look at this paper. But what we want here is to work really in the DLS regime. So how can we know if we're doing the right experiment or not? Well, first, you can have an estimation on whether you're working at the right concentration or not by observing autocorrelation function of your samples upon making a slight dilution. So if you're in the good concentration regime, when you dilute your sample only by a factor of 2, you will have the autocorrelation function in the two situations which do not change. You have the same diffusion time, so you will have the same estimation of the diameter. You have no changes upon the slight dilution. In the intermediate regime, when you dilute your samples, you see that you slightly increase the diameter of your nanoparticle. And in this case, you have to check whether it is due to some heterogeneity of your sample or if it's really due to dilution. And in the last case, where you're working at two concentrated range, you see that you have very, very strong changes in the autocorrelation upon dilution, which means that here you're not working at the right concentration. And you see also that even in the diluted configuration here, you have a characteristic time, which is about 0.2 milliseconds, whereas the correct one, which is measured here on the same sample, is more around 1 millisecond. So you see that you do have an underestimation of the diameter of your nanoparticles. A second way to have an estimation whether you're working at the right concentration or not is to observe the scattered intensity during 1 second, for instance, upon dilution. So here again, if you're in the right regime at the beginning, when you enhance the concentration, you have scattered intensity which increases. And in the DLS regime, you have a linear dependency on the scattered intensity with respect to the concentration. And this is quite logical because the more you put nanoparticles, the more they scatter, and the scattered light is proportional to the number of nanoparticles. But if you start to put too many nanoparticles, you will have still an increase of the intensity here, but this increase is not linear anymore with respect to the number of nanoparticles because some photons are being diffused several times. And if you continue to increase the concentration, then you really observe an opposite behavior with a decrease of the intensity of the scattered intensity in one direction, because in this situation, many photons are scattered all over the place, and you lose the intensity of the photons which are going at the detector. So this, you can see it experimentally also. The first thing is you can observe your sample. So if you take here a sample which is in the good regime for DLS experiment, you have a sample which is quite transparent here, and you only see the beam that goes through the sample. And you have here the incident beam, here the transmitted beam that you see sometimes, and you really see the ray of the lasers that goes through the sample. Now, if you remove the sample and you put one which is more concentrated, you see that the laser now seems to be thicker. So this is due to the image which is a bit blurred, the image of the laser which is a bit blurred due to the beginning of multiple scattering events. And when you change again the sample to put a higher concentration solution, now you don't even see the beam anymore. You just see the light that goes all over the sample. The sample is not transparent anymore because the photons go everywhere into the sample. And this is really a blurred, you don't even have an image, you just have multiple scattering image. This is very typical, like when you look at some milk, you have the impression of having a white or a green, when the laser is green, a green sample due to the diffusion, the multiple diffusion of the light by the nanoparticle. So of course, when you have colloidal solution, the nanoparticles are not strictly monodispersed. They have different sizes. And the size dispersion of the nanoparticle may be characterized by what we call a distribution function, P, which in fact corresponds to the different probabilities of having a diameter d, a particle of diameter d in the solution. So the most likely probability is the highest value here of P, and it is usually related to the mean value of the diameter. And of course, because you have a relation between the diameter of the nanoparticle and the decay rate gamma, you will have also a probability of measuring a time gamma, which correspond each value corresponding to a value of the diameter of your nanoparticle. And it is this distribution to which we have access via the experiments. Now, as for the autocorrelation function, this autocorrelation function, taking into account the polydispersity of the nanoparticle, is now equal to the sum of each exponential decay corresponding to one size, so to one gamma, which is ponderated by the probability of having such a gamma. So also to the probability of having a certain d in the nanopart in the solution. The cumulative method is used to simplify this expression, and you can linearize it and have such expression here, where you find again the baseline, the geometrical factor a here, and you have an exponential decay, which depends now on the mean value of the decay rate, which corresponds usually to the mean value of the distribution here. And you have a term mu2 and mu3, where mu2 is the second order of the centered moment of the distribution, also called the variance, and which is related to the width of the distribution. And you have a centered moment of order 3, which corresponds now to the asymmetry of the distribution of the decay rates. So now, if you want to, you can also do the data fitting using not the monodispersion formula, but the formula obtained from the cumulative method. And in the same manner as previously, you do now a least square fitting of the data, but using this expression for the autocorrelation function. And you see that the obtained fit, which is the red curve here, is now in much more nice agreement with the data than previously. And here again, you can display the parameters which have been used by the software to calculate this expression. And you have access to the different parameters A, B, the mean average of gamma, mu2, and mu3. So once you have that, you have a very nice fit, and you have these values. So the mean value of gamma, the variance, and you can calculate from this what we call the polydispersion index, which you find in most of the commercial setups, which is simply the ratio between mu2 and the mean value of gamma to the square. Now the question is, what do we do with these parameters? How do we obtain the diameter of the nanoparticles using these parameters? The first step to obtain the distribution of the diameter of your nanoparticles is to be able to calculate the distribution of the decay rates G of gamma. However, the latter cannot be directly calculated from the moments or the centered moments we have obtained from the experiments. And to do so, we first have to assume a profile, for the distribution. So the most common distribution which are considered usually is the log normal distribution and some other distribution that we will see further on. And from this assuming of the profile of the distribution, we can calculate them. And then the problem is that we want the distribution of the diameter, not the distribution of gamma. So we have to find a way to be able to calculate this distribution of the diameters from the one of the decay rates. And to do this, we can either take advantage of the fact that both distributions are normalized, so that you have a relationship between the two distributions, and you can calculate one knowing the other and vice versa. Or you can express the moment of the distribution of the diameters as a function of those that you have determined experimentally from the distribution of the gamma, and then assume a profile and calculate the distribution of the diameters. I will not go into much of the details of these procedures, but you can refer to this article if you're interested in the topic. In practice, what does this look like? If we consider, for instance, that we have a normal distribution, which is a Gaussian distribution that writes as the following for the decay rate. This distribution depends on two terms, the mean value of gamma, which is obtained from the experimental fitting of the data, and a term sigma 2, which is equal to the variance of the probability of G that you also have obtained from the fitting of the autocorrelation function. So with the results of the fitting, you can directly calculate the probability, so the distribution of the decay rates here for a value of a mean value gamma of 960 and a polydispersion index of 0.1. And by doing a change of variable, you obtain the size distribution for the diameter. You would find here 244 nanometers with a full width at middle height, which is quite large. If you want to know the effect of the polydispersion index, we can calculate the same thing with a smaller polydispersion index, half smaller, so 0.05, and you see that the dispersion of the nanoparticles is now much smaller. You have a full width here, which is very, very narrower than the previous one, and this can also shift a bit the average value. And this is why in most of the experimental or in the literature, you can find that for polydispersion index smaller than 0.05 you can consider that you have a monodisperse solution because you see that the width of the distribution is quite narrow. Now, taking into, you can also take a log normal distribution. So it's a distribution which is normal, but when you have your variable x, which is expressed as a log in log scale. So in this situation, you have this distribution, which will depend on also a term sigma, which is related to the polydispersion index you have measured from the data, and a term mu, which depends on gamma and on the mean size, on the mean value of the decay rate. So here again, you can calculate this distribution from your experimental parameters, and you obtain a different distribution from the previous one, but that resembles since we're using the same parameters. And you see here that we obtain a mean diameter which is slightly smaller than the previous one, and also a dispersion of full width at middle height. So here an inaccuracy or a dispersion of the nanoparticle size, which is much smaller. So you see that you have quite differences between the two distributions, this one and the previous one. And this does not come from the experiment. It just comes from the choice you make from what you assume to have as a distribution of the size of your nanoparticles inside your solution. And here again, if you reduce the polydispersion index of a factor 2, you see that you have an influence on the parameters you calculate. Finally, a distribution that you can use that was proposed by Pecora and collaborators some years ago is the Schulz distribution, where here again, this distribution right here as the formula which is given here, and depends on a factor z, which depends on the polydispersion index that you have obtained from the experiment, and again, the decay rate that you also have obtained from the experiment. So with these values, you can calculate the distribution of the decay time and obtain that of the diameters of your nanoparticles by doing your change of variable. Here again, we see that you have slightly different values than for the different distribution and an effect of the polydispersion index. So this trend is always the same, but you do not have exactly the same values. So you have to take care, to be careful with the accuracy of the size you actually think to measure. You have to keep into mind that this size estimation depends on the choices you make or the commercial apparatus makes for you. And so DLS is quite good for having an estimation of the size, but it's not, the accuracy is not at the nanometer. You have to be careful with not being too precise on what you obtain, because as I showed before, you see that the values obtained for the mean size of the diameter quite depends on the distribution you have been choosing.